morning, students, and welcome to session 6 of wave mechanics. So hope you followed the last session where we started discussing about superposition of waves, and we saw the first type of superposition involving interference. Okay, so we will take a quick recap of that definition and all that. And of course, the earlier part, hope you understood properly the questions we've discussed related to reflection of pulses, reflection of waves from a rigid or a flexible boundary, and then before that all the fundamental properties of waves like power, wave speed, etc. Things like that. Okay. So let's begin the session with a quick recap of the concept of interference. So we saw that the necessary condition for interference is that there should be superposition of what we call coherent waves. Traveling in the same direction. So of course here we are talking about one-dimensional transverse waves. But we see the definition is almost universal. It's similar for sound and light also. So coherent waves traveling in the same direction when they superimpose, it results in an equivalent amplitude or net amplitude. And identical frequency superposing waves. So this net amplitude, depending on the phase difference between the incident waves. So this particular property is called interference. Okay. So we saw that if we have one wave then the second wave should be of same frequency, so therefore same angular frequency omega, and if their angular frequencies are same, their angular wave numbers will be same because they are passing through the same medium. So omega by k or f lambda is the common value of square root t by mu. They are both propagating through the same medium, but there might be some phase difference, delta phi, let's say. So then the resultant becomes some net amplitude into sine omega t minus kx plus some resultant phase term, where we saw that the simple way of remembering this is the phasor diagram method. So if this phasor represents the first wave's amplitude, then the second wave's amplitude will be represented by a phasor arrow, which is at a delta phi phase difference T2, and the resultant amplitude will become the third side of this triangle, and this will be the resultant wave's phase. Okay. So that E net is given by that familiar formula from vector algebra. And okay. Now a couple of more things we can keep in mind. Okay. So since power is equal to half square root p mu into omega square a square, so this formula E net is equal to square root of E1 square plus E2 square plus 2E1 A2 cos delta phi also indicates that the net power P1 plus P2 plus 2 times square root P1 P2 cos delta phi, where P1 like that P2. So if the individual waves had been operating, then they would have been transmitting this kind of power. But their superposition is resulting in a net power which is proportional to the net amplitude square. Hence, this is the net power propagating as a result of the interference of Y1 and Y2. So this is not like anything exceptionally different or anything. It's just writing the formula of net amplitude, which we are already familiar with, in a new form. Okay. So up to this phasor diagram you have seen last time. So that's just a recap. But this is something that you can note down now. This part. So just make a quick note of this. Okay. Also, people, hope you are working out questions and you might be having some doubts and things while working out questions. So you can discuss with me this week. I will keep the next session again next week mostly as a problem solving session. Today I want to complete the remaining theory part of this chapter as much as possible. The transverse waves on a string, this chapter's theory part, I want to complete that today so that next lecture we can probably keep as an entirely problem solving kind of lecture. And the next one after that we will start with longitudinal waves or sound. But in the meantime, if you are solving questions and you are having any difficulty, you can keep sending me the doubts. I will help you out with hints and things. Of course, another important implication from this formula you've seen is that the net amplitude cannot exceed the sum of the amplitudes and cannot be less than the difference of the amplitudes. Okay, so hope this formula for the net power is clear to all of you. This one. Okay, another situation we come across very often is can the destructive interference be such that, yes, Suti, what is the full question? Yes, there is zero or amplitude can become zero in destructive interference. If A1 is equal to A2 and there's destructive interference, in fact, that's the point I'm coming to next. If the incident waves or the interfering waves have the same amplitude. Okay, suppose that amplitude is E naught. Then we can use a shortcut formula. This becomes the formula as is after substituting A1 equal to A2. So this can be further interpreted this way, or further you can simplify it this way. Now cos delta phi can be written as 2 cos square delta phi by 2 minus 1. Okay. So using that half angle identity over here, finally you see you get a very convenient formula. It becomes 2 times E naught mod of cos delta phi by 2. Because this 2 and 2 cancel out. All right, so this or this becomes the equivalent formula when you're dealing with this situation. The interfering waves are having the same amplitude and therefore the same power. So you can see destructive interference here results in 0 amplitude and 0 power. So they just absorb each other's power. In such a case, this is the range of power and amplitude. Okay, so hope this special set of formula is clear. So this can be used like a shortcut formula. Every time your amplitude of the incident or the interfering waves is same, you can avoid that lengthy formula and just use this formula. Especially later in things like wave optics and all that, we'll see this formula is very useful. Because very often we are looking at superposition of waves of same amplitude, interference rather of waves of same amplitude. Okay. Now moving on, so last time we were also seeing that the phase difference delta phi, it can depend on path difference, delta x, so it becomes k into delta x, can depend on also time difference. So what we mean by time difference delta t is, time difference is a situation if occurs that if the sources of the interfering waves are not synchronized. Okay. And remember, by sources we mean what? They are simple harmonic oscillators. So the individual simple harmonic oscillators which are creating the waves, which which are interfering are not in sync. They are having same frequency, but they are not in sync. Then that creates a time difference delta t, and that time difference corresponds to a phase difference of omega delta t. So it can be as a result of path difference, which we saw last time, but it can also be as a result of time difference, or it can be as a result of a combination of the two things. Okay. So let us see an example to understand this better. So similar type of situation that we saw last time, that you have very long string stretched out with some tension, so it's going to infinity on that side. Now here at x equal to 0 and at x equal to d, two simple harmonic oscillators are attached, which are creating oscillations along the y-axis. And we have to understand the net kind of displacement at x equal to x, where x is greater than d. So this is a light thread under a tension E equal to, let's say, 1000 newtons, and having a linear mass density, let us say 4 gram per centimeter. Now S1 and S2 are simple harmonic oscillators with amplitudes, let's say 1 millimeter and √3 millimeters each, and identical frequency of f equal to 1 kilohertz each. So if S1 is started from mean position along positive y-axis at t equal to 0, and S2 is started again from mean position along the positive y-axis, but at t equal to say 0.25 milliseconds. So there's a slight delay between the two, and this one is started at t equal to 0. This one is started quarter of a millisecond later, and this distance d is equal to, let us say, 33 centimeters. Want to find the net amplitude of oscillations at the point E. So let me just minimize this so that you can go through the whole question. change d to 3.3 centimeters. Okay, instead of. Okay, Ninad, I'll scroll up to the previous note. You can just down this part. Okay, so this is done. Now just so you can say, take the same kind of approach to this question that we did last time. But only thing is when you write the wave equation, you'll also have to take into account that they are not started synchronously at t equal to 0. Okay, they are started asynchronously. The second one is started with a slight time delay compared to the first one. So you do the question in the same way. You try to write the wave equation due to the source S1 and the wave equation due to the source S2 and see what happens as a result of that. Okay, we will show at a later stage. I will show you how you can do this question without writing equations and all that by directly writing the phase difference. But since we are kind of new to these type of situations, let us do it in a more fundamental way to begin with. Yeah, I have got some answers. Let me check that. Ganesh, you're getting root 7 millimeter. Okay, let me check. Okay, so first of all, let me look at the wave speed square root p by mu. So that is square root of 10 raised power 3 divided by 0.4. So that will become 10 raised power 2 by 2 or 50 meters per second. And frequency is given to us as 1 kilohertz or 1000 hertz. So the wavelength will become 5 centimeters or 50 by 1000 meters. So that is 5 upon 100. So your omega is 2000 pi radians per second, and your k is 2 pi by 5 radians per centimeter. Okay. You can also write this as 2 pi radians per millisecond. Also write it in this unit. That's also fine. Just like we've written this in radians per centimeter. So now you can see that your source S1, okay, this one's equation will become E1 sine omega t minus kx. This is the disturbance at the point P due to S1. Okay. But Y2 on the other hand will become E2 sine omega t minus delta t because it started with a delay. Okay. And it's traveled a distance x minus delta x like this, because the delta t is equal to the time delay which was given, because the source S2 started with a delay of delta t compared to S1, which started at t equal to 0. And of course, the path it's traveling, so that delta x is equal to t, because the source S2 is at x equal to t, and the point P is at x equal to x. So the path it is traveling is x minus t. So these are the individual waves created by S1 and S2. So just understand the steps up to here first once, then it becomes very easy. Yeah, Ganesh, I think you got it correct now. So here we know that E1 is 1 millimeter and E2 is root 3 millimeters. So might have added omega delta t with k delta x to get the phase difference, but actually it's the difference of the two. No? Right, plus minus mistake that. So that is why writing the wave equations individually is a very safe option. So I will tell you a shortcut method also where we don't have to do so much work. Okay, so now if you compare the two wave equations, so hope these aspects are clear to all of you, because this is the critical thing over here. E t minus delta t in comparison to E t क्यों हो रहा है? Because this has started at t equal to 0, whereas this has started after a delay of delta t. So at some time t, this source has been oscillating only for t minus delta t, whereas this has been oscillating for t. Okay. Similarly, the wave from here has traveled x, but the wave from here has traveled only x minus d. So like that. So keeping this in mind now, you can see that the resultant displacement will become y1 plus y2, which we can further write as E1 sine kx minus omega t plus E2 sine kx minus omega t plus some phase difference, okay, which will ultimately result in some net amplitude into sine omega t minus kx. But actually it hardly makes a difference, but still should be technically correct. So this resultant will become omega t minus kx plus some resultant phase. Okay, so let's see. So here, by comparison, above you could see that delta phi was equal to how much? It was equal to kd minus omega delta t. Let's see. If you just open up this term, this term you can see can be written as omega t minus kx plus a certain phase term, where that phase term will become plus k delta x minus omega delta. So now let us substitute the values. So that becomes 2 pi by lambda. Now lambda was how much? It was 5 centimeters, and this one we are taken as 3.3 centimeters, and omega was 2 pi in radian per millisecond, multiplied by delta t was 0.25 milliseconds. Yes, we will write it as 10 by 3, correct, Ganesh? Okay. We can write this as 2 pi by 5 into 10 by 3 minus 2 pi into 1 by 4. So 2 pi into 2 by 3 minus 1 by 4. Okay. Or you can see basically it is 120 degrees minus 90 degrees. That is 30 degrees. Oh, sorry, no, my mistake. It is 240 degrees minus 90. So that is or from here you can see it is 8 minus 3, so that's 5 by 12, so 5 by 6, 5 by 6. So this makes life very simple. see that and delta phi is this. So it is 1 square plus root 3 ka whole square plus 2 into 1 into root 3 into cos delta phi will become cos 5 pi by 6. So that is minus cos pi by 6. That is minus root 3. So 1 millimeter becomes the net amplitude. Okay, and that's the only thing that I've asked here, so it's fine. Otherwise, if required, you can find that epsilon also by that tan inverse formula. So the critical thing here was understanding the relationship between phase difference and time difference. This one was a critical thing here. Yeah, so the phase difference depends in this case both on the time difference and the path difference. See, the sources, they are not at the same position. Na? So the two waves are also traveling different paths. Pehla wala wave, okay, so I think because of your internet issue, you missed this part, so let me just explain this. So देखो, यहाँ पे you'll get the whole thing. The first wave x equal to 0 and it started at t equal to 0. So this source S1, this was at x equal to 0 and it started at t equal to 0. So this term becomes like this. But this one, this source was at x equal to d also. No? So therefore its path is x minus d instead of x to that point. And plus it is started at t equal to delta t. So it's 0.25 milliseconds. And this was 3.3 centimeters. So therefore, the time. So both the factors are playing a role in creating phase difference between the two waves. The fact that they are not synchronized, that is also creating a phase difference, and the fact that they are not traveling the same path length. Okay, good. So now let us I mean, extra work in the sense of writing the two equations. So that's not necessary actually. We can understand the phase difference logically also. So I'll come to that. But first, just make sure this whole calculation is clear to all of you. Okay, so hope this is clear. Now the whole thing is that can we calculate the phase difference directly? So can we calculate the delta phi term directly without writing all these equations? The answer to that is yes, we can do it logically. So what is happening here is, see, S1, S2, this is starting at t equal to 0, this is starting at t equal to delta t. Okay. So and this distance is d and this point is p. So what is happening is that, okay, the wave from S1 is delayed by a phase of k delta x, where delta x is equal to d, okay, because it's traveling extra distance of delta x equal to t. That is the first point. Okay. But on the other hand, the wave from S2 is delayed because it starts at delta t seconds later in comparison to S1. Okay. So therefore, my net phase difference delta phi should become k delta x minus omega delta. Okay. Whereas suppose we had a situation, so I'll come back to this, but suppose we had a situation if S1 was started at t equal to delta t and S2 was started at t equal to 0, then in this case what would have happened? S1 is delayed because it's traveling delta x equal to d extra, it's traveling an extra distance to this point p, okay, plus it's delayed in time by delta t. So in this case, the phase difference would have become k delta x plus omega delta t. Okay. Because here, if you wrote the wave equations, you would have seen your y1 would have been e1 sine and your y2 would have been e2 sine omega t minus k into x minus dx. So it's like, this one would have been e1 sine omega t minus kx minus some alpha, and this one is e2 sine omega t minus kx plus some beta. If you compare, the phase difference between them, delta phi, is equal to alpha plus beta, which is your omega delta t plus. So this is the fundamental way of understanding why that's happening, but you can just logically understand whether the two factors of path difference and time difference, they are contributing in such a way that they are adding to each other or they are trying to cancel each other. So in the first case, they are trying to cancel each other. You can note down this point. Then come to the equation below. So this is important. Okay, people. So hope this point here is clear to all of you, because it's going to be really crucial in chapters ahead also. When we discuss about interference of sound waves or later interference of light as an electromagnetic wave. This realization of how phase difference depends on time difference and path difference, and how they are either contributing to each other by adding or cancelling, or adding or subtracting rather. That very important aspect in solving the problems. Sudhir, I didn't understand. The first case, why can't it be omega t minus kx? Hey, because यहाँ पे तो ही हो रहा है. In this case, actually, this one is this. Y1 is E1 sine omega t minus kx, because the source S1 was started at t equal to 0 and plus is traveling the full distance x. This point is x equal to x. This point is x equal to t. This point is x equal to 0. Okay. But in the example I have written below, this source is not started at t equal to 0. It was started at t equal to delta t. So here this one is started with a delay delta t. So इसका time factor क्या हो जाएगा? T minus delta t. And plus ये इसका path length भी d से कम है. So that's why when you compare this and this, you can see your phase difference in between this. So this thing, instead of writing the equations, I'm just saying understand it logically. Actually, that phase factor. See, this is coming from the derivation of this equation. See, this source has started oscillating at t equal to 0. So it is y of the source S1 is E1 sine omega t. Because this started oscillating at t equal to 0 from the 0 phase that's given to us in the question. So now as this wave is traveling, when will this point P start oscillating? It will start oscillating after the wave has traveled through a distance x. So इस पे क्या हो जाएगा? The displacement at the point P will become E1 sine omega into t minus x by v. So that's how this becomes E1 sine omega t minus x. Okay. Now in the general equation of the wave, omega t minus kx and kx minus omega t are always interchangeable, but it makes a difference in phase. So E1 sine omega t minus kx can always be written as E1 sine kx minus omega t, but with the additional phase factor of pi. So that's why this and this in general are interchangeable in your general equation. Okay, Samyak, hope your point is hope this point is clear. And hope you've written down that first example. Now, for example, in this case, if the first source was given a delay compared to the second one, then the delay would contribute to more phase difference, because already the wave from S1 is traveling an extra distance, so it's taking more time to reach the point P. Plus, you're delaying the start of that source. So the two factors omega delta t and k delta x are actually adding to each other in creating phase difference. Whereas if I had given S2 a delay instead of S1, then they would have tried to cancel each other, the two factors, or they would have subtracted from each other. Because the delay given to S2 would tend to delay S2, whereas the extra path length traveled by S1 is delaying S1's wave. All right, so hope this aspect is clear. Okay, next let us look at a situation where we have more than two waves interfering. Okay, so suppose we have waves from three simple harmonic oscillators given by these equations. Superimpose at a given point x equal to x. So find the resultant net amplitude due to their superposition. So you can go with either a trigonometric equation kind of method for adding them, or you can go with also the phasor diagram, whichever you feel is more convenient. You can use that. Any number of tricks you can use. You people are more well versed in trigonometric equation solving and all kinds of tricks than even I am. So you can try whatever method you comes to mind. And otherwise, you always have the phasor diagram method to fall back on. Yes, Ganesh, Somadip, Samyak, your answers are correct. So here you can go by either the phasor method. If you go by the phasor diagram method, you will see that something like this. Yes, Ninad, correct. The first one is this, then second one in comparison is like this. The third one in comparison becomes something like this, let's say. It becomes pi by 6. So your resultant amplitude will just become this whole. That will be A naught plus root 3 A naught into root 3 by 2. 4 A naught will become the net amplitude. Very simple, nothing exceptional about this. Or you can also go by the trigonometry method. So algebraically, if you solve this, so you can do like this, that suppose you take the whole term omega t minus kx as theta. No, it is neither constructive interference nor destructive interference. Because constructive कब होता है when the phase difference is even multiple of pi, and destructive कब होता है when the phase difference is odd multiple of pi. So this is that in between situation, neither constructive nor destructive. You can see the phase difference between y1 and y2 is actually plus pi by 6. The phase difference between y2 and y3 is pi by 3, or between y1 and y3 is again pi by 6, like that. So this is A naught sine theta plus A naught sine theta plus pi by 6. So root 3 plus root 3 A naught sine theta minus pi by 6. So one of the tricks you can use here is that since these two are having the same amplitude term, you take that common and use the sine A plus sine B formula. So this will become 2 times sine of this plus this by 2. So that will become sine theta, and cos of this minus this by 2. So that will become cos pi by 6. that will become E naught sine theta plus root 3 by 2. Now cos pi by 6 is root 3 by 2, so that is root 3 sine theta. So E naught 1 plus 3 sine theta. This is yet another way of doing the problem. Okay, understood now. So had this been constructive interference, then your phase difference would have been 2 and pi types for each of them. So your resultant amplitude would have become A naught plus root 3 A naught plus root 3 A naught. The maximum possible amplitude for the superposition of these three is the sum of their amplitudes. But here 4 A naught is less than 1 plus 2 root 3 times A naught. Okay, so people hope this is clear. By both the methods, the phasor diagram method, which generally speaking is the easier method, or the algebraic method. Okay, now let's come to another type of superposition, which creates what is called standing waves. Okay, yeah. So just a minute. We'll come back to this. Right, Sudhir. So hope this is clear now. Okay. So now another category of superposition. See next. The case of what we call standing waves or stationary waves. So this can happen as a result of superposition of two waves of identical amplitude and frequency, but traveling in opposite directions. Along a stretched string. So here we are obviously talking about transverse one dimension. So let us understand, as we study this in more detail, we'll understand why it is called a standing wave or why it is called a stationary wave. So imagine on a string from one side, from a source very far away on this side, you have a wave traveling like this of amplitude, let's say A naught, and frequency F. And from a source very far on the other side, you have another wave, but traveling in this direction. Same amplitude, same frequency, but traveling in the opposite direction. And suppose we have written the equations for the waves as E naught sine omega t minus kx for this one, and this is E naught sine omega t plus kx plus some phase term. Now to make this easy, let us take the case where this phi is some 2n pi, suppose. Okay. Just to make the understanding easy, we are taking the special case where this phase term is actually 2n pi, so it's equivalent to 0. Equivalent to 0. So now at any given point in between, the net disturbance is the superposition of these two. So it is E naught sine omega t minus kx plus E naught sine omega t plus kx. Because we've taken this into account that our phase constant is 2n pi. So the resultant disturbance now becomes like this. It becomes E naught sine A plus sine B type of term, which when we solve, get like this. 2 A naught sine of this plus this by 2, so that will become sine omega t into cos of this minus this by 2, and cos is an even function. So cos minus kx is the same thing as cos kx, which is this. So this becomes the equation of the resulting, what we call standing wave. The resulting standing wave, okay, or stationary wave equation. So you realize the moment you look at the equation, that is not the equation of a traveling wave anymore, because there is no linear term in kx and omega t. So you understand immediately that this y net is not of this type. Okay. So that means the superposition of y1 and y2 results in a type of disturbance, or you can say wave pattern, which is not a traveling wave, and that is why it is called a stationary wave. Now, if not a traveling wave, why it's called a stationary wave, that also you'll understand in more detail, but at least you can see by just looking at the equation that it is not a traveling wave. because the equation doesn't match the general equation of a traveling wave. So Shruth, in the previous 3-wave interference question, if you want to use the formula for that, net amplitude is square root of a1 square plus a2 square, that one, you'll have to add 2 equations at a time. So you'll have to add y1 plus y2. You'll get some resultant wave equation. For that, you'll need the phase term also. Then you will have to add that resultant with y3. So you'll have to use that formula twice. You understand? So what you'll end up doing is you'll do this phasor addition first. This was like this. Calculate this resultant phasor, and then do the addition of this resultant phasor with the third one, which would have given you this. So it would become a more complicated question. Yes, we get the resultant phase. The resultant phase is this one, the tan inverse of a2 sine phi upon a1 plus a2 cos phi, that one. So it's like double the work. You have to first add the equation 1 and 2 and get the resultant amplitude and the resultant phase. Then use that resultant amplitude and phase to add it with the third one. So that becomes the unnecessarily lengthy kind of method of solving. So that's why the phasor diagram method usually is easier. And in this particular case, just using trigonometric kind of trick of solving the, like a trigonometric equation, you're solving it, because the terms were symmetrical. One was plus pi by 6, the other was minus pi by 6. So, and the amplitudes of those two were also the same. So we were able to separate it out and use the sine E plus sine B formula. So that became like another trick method. But generally speaking, the phasor diagram method is the easiest. Okay, so now come to this standing waves concept. So first of all, the definition of stationary or standing waves. It is the type of wave pattern which can result from the superposition of two waves of identical amplitude as well as frequency. Remember, in interference, amplitude need not be equal, but here for stationary wave production, it is necessary that the two superposing waves have same amplitude also, not just identical frequency, and they are traveling in opposite direction, not traveling in the same direction. They are traveling in opposite directions along a straight string. So they will superimpose to give you the situation which we have solved as this now. Yeah, this can happen as a result of reflection at a boundary. This can happen because of that. Okay. So if you have a situation, but then the reflected wave should have the same amplitude, okay, which is rarely the case because there can be transmission also. So this situation can be as a result of continuous reflection from a boundary. Okay, so now let us understand more about this equation by exploring how y is dependent on x and t. So now if you see this equation of the standing wave, y is a function of x and t such that it is 2a naught. I'm just interchanging the kx and this thing terms. Okay, so it's cos kx into sine omega t. So if you notice this equation, what information it is giving us? It is giving that for a particular point, let's say x equal to x naught on the string, okay, y as a function of time at x equal to x naught is becoming 2a naught cos kx naught sine omega t. So it is like this. So you can see that the displacement of that point, it is an SHM, the simple harmonic motion with omega equal to 2 pi f, okay, and amplitude equal to mod of 2a naught cos kx naught. Okay. So therefore, any medium particle is in SHM with angular frequency omega, but amplitude, which is position dependent, because the amplitude is this thing. So therefore you can see that the amplitude at any point can be as low as 0 also, and can be as high as 2a naught also, and that amplitude depends on its position, depends on x, okay, because that amplitude is equal to 2a naught mod cos kx. Therefore you can see that the amplitude is maximum equal to 2a naught at x such that cos kx mod is 1, or cos kx is plus minus 1. So x is equal to 0, lambda by 2, lambda, 3 lambda by 2, so much, because that means that kx is equal to 0, pi, 2 pi, 3 pi. Okay. Whereas the amplitude on the other hand is minimum is 0 at x such that cos kx is 0. So kx should be pi by 2, 3 pi by 2, 5 pi by 2, and so on. So x would be equal to lambda by 4, 3 lambda by 4, 5 lambda by 4, 2n minus 1 lambda by 4. So later we'll see that these kind of positions are called nodes, and these kind of positions are called antinodes. But that we'll see after drawing the snapshot pictures and all properly. First, you just note down this first point of the interpretation of the standing wave equation. Okay. So Okay, so just go through this and note down the key points. So already you understood that it's not the equation of a traveling wave anymore, because the argument of the function is not linear in x and t. It has a separate kx term, it has a separate omega t term. But now if you look at these terms, what is the omega t term? It is sine omega t. So that is indicating that in terms of time, there's an oscillation with angular frequency omega. There's an SHM with angular frequency omega. But what is the amplitude of that SHM? So for that, you look at what term is attached with sine omega t, and you see the term attached with sine omega t is actually x dependent, because it is 2a naught cos kx. So magnitude of that term becomes the amplitude of the oscillation. So you're seeing that unlike traveling wave, where the amplitude of all medium particles is the same, which is E or A naught or whatever, here we have different medium particles having different amplitudes. In other words, the amplitude is position dependent. Okay. That still doesn't give us an explanation of why it is called stationary wave, but it's just showing you an important property of the type of disturbance that is going through the medium right now. The disturbance is such that all medium particles are in SHM with angular frequency omega, but they are having position dependent amplitude. Yeah, Uday. Right, so this concept of position dependent amplitude should be clear from this, and you can see that this amplitude varies between the maximum value of this much and the minimum value of this much. And for example, for the above wave equation, which was 2a naught cos kx sine omega t, the wave equation was this. From this equation, we can see that which positions exactly are having maximum amplitude. So there are positions at which the value of x is 0, lambda by 2, lambda, 3, lambda by 2, etc. like this. Whereas which positions are having minimum or 0 amplitude, they are the positions at which x is lambda by 4, 3 lambda by 4, or any odd multiple of lambda by 4. So more about this we'll understand when we look at the graphs of the snapshot pictures. Okay. Yeah, sorry people, my connectivity is just gone for a moment. Just hang on, screen will be back. Just had a drop in internet connectivity. Right. So coming back to this, this was our wave equation. So here omega, which is 2 pi f, can also be written as 2 pi upon time period. So time period is 2 pi by omega, and similarly lambda is 2 pi by k, because k was equal to 2 pi by lambda. So keeping these two things in mind. Okay. Now suppose we want to look at the snapshot at t equal to 0. So it becomes e cos kx sine 0. So sorry, 2a naught. So that just becomes 0. Suppose we want to look at the snapshot at t equal to 1/8 of the time period. So this becomes 2a naught cos kx sine pi by 4 हो जाएगा ये, because omega into t by 8 is 2 pi by t into t by 8. So that is pi by 4 or 45 degrees. So this will become root 2a naught cos kx. Similarly, if we look at capital T by 4, this will become 2a naught cos kx sin pi by 2 हो जाएगा. Because similarly, you can understand that omega t by 4 is nothing but pi by 2. So this will become 2a naught cos kx. Then again, we look at it at, let's say, 3t by 8. This will become 2a naught cos kx sin 3 pi by 4. So that's again root 2. So this will become root 2a naught cos kx. Then again, we look at it at, let's say, t by 2. So this becomes 2a naught cos kx sin pi. So that is nothing but 0. For example, in half a cycle, going from 0 to t by 2, we can see how the shape of the medium is changing like this. We plot this next and you'll see. Okay. So if you plot this series of things, just a second. if I plot y versus x at various different times, so for example at t equal to 0, I would have seen that the shape of the medium is just this straight line. This is how it was looking at t equal to 0. Whereas at 1/8 of the time period, it had become cos root 2 a naught, root 2 a naught cos omega t. So that would have looked, let's say, something like this. This is at t equal to t by 8. Then by the time you are reaching t by 4, it's further becoming something like this. Like this. This is at t equal to t by 4. Then 3t by 8 is actually back to this shape. And then t by 2 is back to this shape. Then 5t by 8, if you take, it will then be this kind of shape now. This kind of shape. Okay. And then so 3t by 4, it's here. Then 7t by 8, it will be back here. And then one full time period is back to the straight line graph. Okay. So this becomes this series of, and of course here in this graph, this is a naught, sorry, 2a naught minus 2. So you can see that this is how the snapshot pictures are looking at various different times. So what I'll do is we'll go back to the equations first, and where you've written the equations, you can see the individual graphs also. So here, this is y equal to 0. Then this one is y equal to root 2a naught cos kx. Then this one in comparison, 2a naught cos kx. It's varying between plus and minus 2a naught. This is varying between root 2a naught and minus 2a naught. So that's how the graph keeps changing between these. So similarly, if you now plot at t equal to 5t by 8, this will become 2a naught cos kx sine 5 pi by 4, that will become minus root 2 a naught cos kx. Similarly, you plot at y equal to 3t by 4. This will become minus 2 a naught cos kx. And so on and so forth. The progression goes. Okay? So just make a note of this section first. The snapshots at various different times. And then we will come back to the graphs. So just write down these equations first by substituting the value of t as whatever is written here, 0, t by 8, t by 4, like this. Then we'll come to the graphs and all in detail. first understand how these correspond to the graphs on the right. Then we'll come to the overlap pictures below. So at an individual time, the string is looking like any individual one of these graphs. Okay. So if you sort of take time lapse images of the string and put them together, you will see this the string is like this shape below. Okay, so if you also look at this graph in a little bit more detail, so you will understand that as far as the x coordinates is concerned, this point is of course 0. This point here, this one, this point is x equal to lambda by 4. Then this next point here, where the amplitude is going up to 2a0, this point here is x equal to lambda by 2. Then the next point here is 3 lambda by 4. Like this. Okay, so wave like this, if in general we want to understand its progression with time, so that progression is something like this. If let's say at a certain instant of time, at a certain instant t equal to t, it is 2a naught cos kx sine omega t. So that graph at that particular moment of time is looking like this. Let's say looking like this. This is at some time t, where you can see that whatever this amplitude will be, that value is 2a naught cos, 2a naught sine omega t का mod. That value is, let's say, t. That is c. The graph is varying between minus a and plus a. Also, you can see that it's basically a cos kx graph. So that is why this point will be corresponding to where kx is pi by 2. So that means x is lambda by 2. This point will correspond to where kx is pi. So x will be lambda by 2. This point will correspond to where kx is 3 pi by 2. So x is 3 lambda by 4. And this point will correspond to where x is lambda. So then again add another lambda by 4. Add another lambda by 4. Add another lambda by 4. 7 lambda by 4. 8 lambda by 4 or 2 lambda lengths. So lambda. Now, lambda by 2. Lambda by 2. Now, if you want to see how it progresses from this time to now just a moment later, so it's gone from this to t plus delta t. So this becomes 2a naught cos kx sine omega into t plus delta t. So it's like this term 2a naught sine omega into t plus delta t. ये वाला term जो है, this was a earlier, so this has just become an a plus a small delta. So this graph has just shifted like this. This is how it has progressed from that time to t plus delta t. Okay, then next moment it will shift a little bit more like this. The next moment it will shift till it goes to a maximum of how much? 2a naught. And then it will start coming down. So you can see here that as far as is concerned, at the points x equal to 0, lambda by 2, lambda, 3 lambda by 2, or 2n minus 1 lambda by 2, these kind of terms, the amplitude of oscillation is 2n, because cos kx common is equal to 1. These points. So these points where this is happening, they are called antinodes. Whereas if you look at the alternate set of points, odd multiples of lambda by 4, you can see that cos kx is 0. So their amplitude is 0. So they are fixed points. They are not moving. They are not having any oscillations. So they are called nodes. Whereas these points, they are having amplitude difference. That means they are in SHM with maximum amplitude of 2n and angular frequency. Okay. And you can see that also all the set of points that are between x equal to, let's say, lambda by 4 and lambda by 2, or in general 2n minus 1 lambda by 4 and 2n minus 1 lambda by 2, these sort of points, they have an amplitude which is neither equal to 2a and nor equal to 0. It's greater than 0 but less than 2a. So that is what is showing you that there is position dependent amplitude. So finally, looking at the snapshots, you can analyze and understand that the wave shape does not travel along the strip. In fact, the nodes are stationary points. Hence, it is called a stationary wave. And along the x-axis, the amplitudes which are position dependent vary periodically between the maximum value, which are called antinodes, to the nodes. Such that distance between consecutive nodes, or for that matter antinodes, is equal to lambda by 2. This you can understand from that series, because we saw that the antinodes were at x equal to 0, lambda by 2, lambda, so on and so forth. Whereas the nodes were at x equal to lambda by 4, 3 lambda by 4, 5 lambda by 4, and so on and so forth. So the distance between consecutive nodes, like the first node and the second node, or the second node and the third node, that is lambda by 2. Or the distance between consecutive antinodes, that is between the first and the second and the third, that's also lambda wave. Whereas and node and next consecutive antinode, that is lambda wave. I'll just help you out with a graph over here. So now we can see that these are the positions of the nodes. These are the so-called nodes. So I'll write them as n. So the distance between any two consecutive nodes will be lambda by 2. Whereas these positions are where the antinodes are, in between the nodes. You see that this position here, this position here, this position here. These are the antinodes where the amplitude is maximum. So again, the distance between consecutive antinodes is also lambda by 2. And therefore, the distance between consecutive node and antinode becomes half of that. Okay, so this is the full proper interpretation of the standing wave equation. Explaining to you why also it is called a stationary wave. Just a moment. This is how the wave is progressing from t equal to t plus delta t. In the graph, you can see it's not shifting along the x-axis. It's just the nodes are remaining fixed points. Yeah, I'll come to that. This you've written down, no? So I'll come to the node part. Must understand this. Okay, so let's look at an example here. Waves of frequency 100 hertz traveling in opposite directions of amplitudes 2 millimeter each on a string of tension 250 newtons, linear mass density 1 gram per centimeter, okay, overlap to create standing waves such that x equal to 0 becomes a node. So first of all, if y1 is e sine omega t minus kx and y2 is e sine omega t plus kx plus phi, find the k phi. Of course, that is write the equation for the net disturbances y1 plus y2. Secondly, find the amplitude at x equal to at these three positions. Find the amplitude at antinodes and the positions, that is x coordinate of antinodes Okay, so just try this out. No, Uday, in transverse waves, the amplitude of every point is constant. It's the y coordinate which is varying with time, but amplitude क्या होता है? Amplitude is the maximum displacement of the oscillation. No? So in a traveling wave, the amplitude of every point is the same. It's the amplitude of the wave. But in a standing wave, the amplitude of different points vary. Like the position of the nodes, they simply don't oscillate, so the amplitude is 0. Whereas at the antinodes, the amplitude is maximum, which is twice the amplitude of the individual waves. Whereas at some other in between point, you'll see the amplitude will become whatever that mod of 2a naught cos kx is. So if cos kx or sine kx or whatever term there is over there is such that it is 1 by root 2 or 1 by 2 or something like that, the amplitude will be according to that. So traveling wave has the same amplitude for every point in the medium. Okay, what is different for the different points is just the phase of oscillation. So two particles in a traveling wave which are at a distance of delta x, their SHM has a phase difference of k delta x, but their SHM has identical frequency and amplitude. Whereas in a standing wave, two particles which are at different positions have different amplitudes. Yes, that's correct. Omega is 200 by radians per second. Its frequency is given to you as 100. Yeah, angular wave number will be 4 pi, that's correct. Because your wavelength will be 50 centimeters or half a meter in radians per meter. Yes. And phi is becoming pi. That's correct. Good. Odd multiple of pi. So which one is it? Pi or pi by 2? Acha, you mean pi or 3 pi or like that? Yes, correct. Yes, Ganesh, your final equation is also correct. Very good. So basically, see, we will have to first of all make use of all this data which is given. So the tension in the string is this, and the linear mass density is this. So for these waves, the value of k, first of all, and of course the frequency is 100 hertz. So omega is 2 pi f, so that's 200 pi radians per second. and k is 2 pi by lambda. Now here lambda will become 1 by f into square root t by mu, because you use the equation v is equal to f lambda, so on. So it is 1 by 100 into square root of 250 by 0.1. So you can see that it is 0.5 meter or 50 centimeters. That's lambda. So accordingly, your k is becoming 4 pi radians per meter, or pi by 25 radians per centimeter, however you choose to write it. Okay. So now we have come to a situation where your wave equations are like this. Your individual wave equations, y1 and y2, relate them now. So y1 is 2 millimeter sine 200 pi t minus 4 pi x. And for the moment, let's just write that as E naught sine omega t minus kx. And y2 is 2 millimeters sine. गणेश वो सेंटीमीटर में आएगा, जो एंटी नोड्स का पोजीशन यू राइटिंग, आई थिंक इट शुड बी इन सेंटीमीटर, जस्ट चेक वंस. सो ओमेगा टी माइनस, yes, now it's correct, kx plus some phase constant, where we don't know that phase constant right now. So plus kx plus 5. So our net y now will become E naught sine omega t minus kx plus sine omega t minus plus kx plus that unknown phase confined. So now you do the same process, but remember that there's that additional phi now, which we had earlier taken to be 0 by default, but here it's not that case. So this will become 2 sine e plus b by 2, so that will become omega t plus phi by 2, and cos a minus b by 2, so that will become kx plus phi by 2. So this is the net. Now from this you can see that therefore amplitude at any position as a function of x is nothing but 2a naught cos kx plus phi by 2 come on. So it's this. Now given, so this is a very important step now. X equal to 0 is a node. Okay. So that means amplitude at x equal to 0 should be 0. Okay. So that tells you that cos phi by 2 should be 0. Okay. So this is the amplitude as a function of x, and we know that at x equal to 0 the amplitude should be 0. So that means that 2a naught cos phi by 2 should be 0. That means cos phi by 2 should be 0. That means phi by 2 could be pi by 2 or 3 pi by 2 or 5 pi by 2 or anything like that. So in general, we can say phi should be an odd multiple of pi, but we can take the easier value of pi, or it could be any 2n minus 1 pi. But let's start with this. And given that now our standing wave equation will become 2a naught sine kx plus pi by 2 cos omega t minus pi by 2. As a term, or our standing wave equation is becoming 2a naught. Now this cos omega t plus pi by 2 we can write as minus sine omega t. So minus, oh sorry, this term was omega t, this term was. Okay, so this term becomes sine kx, but with a minus sign of course, and this term becomes cos omega t. Write the net equation like this, where A naught is equal to 2 millimeters, K is equal to pi by 25 radians per centimeter, and omega is equal to 200 pi radians per second. So that is this part done. So you can now see that the amplitude at any point, but wait, before that we wanted to calculate. So we've got the equation of the wave and all that. Got this. Now we wanted to calculate the amplitude at 12.5, 50 and 25 by 4. So let's do that. So amplitude at any point as a function of x is 2a naught mod of sine x. So you can see that amplitude at x equal to 12.5 centimeters is 2a naught sine of this. So it is in fact equal to 2a naught. It is 4 millimeters. Amplitude at x equal to 50 centimeters is 2a naught sine is 0. And similarly, amplitude at x equal to, what was it, 50 by 25 by 4. Yes. So this becomes the second part solution. And from this you can also see that since the amplitude is proportional to mod sine kx, so you can see that modes are where kx is equal to 0, pi, 2 pi, n pi, So x is equal to 0, lambda by 2, lambda and lambda by 2. So that is x is equal to 0. Now lambda was 50 centimeters. So 25, 50, 75 or n times 25 centimeters. And antinodes, those are where sine kx, a mod is 1. So sine kx is plus minus 1. So kx is pi by 2, 3 pi by 2. So x is going to be correspondingly lambda by 4, 3 lambda by 4, 5 lambda by 4, or any odd multiple of lambda by 4. So x is equal to 12.5, 37.5, 62.5, any odd multiple of 12.5 in centimeters. These are the position of the antinodes. So that's the final part of the question. Okay, so the difference between this question and the standard derivation we had done was here the wave coming in the opposite direction has a phase term phi, and how we calculated the phase term phi was from the information given in the question that the superposition is happening in such a way that the x equal to 0 position on the string is finally coming out to be a node. So the amplitude at x equal to 0 should come out to be 0. So we use that information to back calculate what the phase constant phi should be. Right, so that's what we did in this question. This from this given condition, we got the value of phi, and then the rest is just proper calculation of sine and cos terms and things like that. No, so that's the point. Somebody here. Nodes are at n lambda by 2. Right. Okay, so Ganesh, hope the nodes and antinodes both are clear. No? All right, people. So we conclude here today. Okay. So we have still a little bit of work left in theory in this. Next time we'll be looking at the resonant modes of vibration, or what we call the modal frequencies of vibrations for a string which is between two finite boundaries, or a string of fixed length between two rigid boundaries. If we make it vibrate, then what are the modal frequencies or the resonant modes in which it can vibrate, which is related to standing waves, because that kind of situation also creates standing waves in a string. And we'll see how to relate that with this method of standing waves that we've discussed today, where we are not talking about a string vibrating between two fixed points, but rather we are talking about an infinitely long string, but two sources on the opposite sides creating waves traveling on the opposite sides. The frequency same and amplitude same, those kind of waves superimposing to give standing waves. But next time we'll also see that standing waves can also be created by the modal questions. Yes, I will send you another block of questions to do with interference, standing waves, and also revision of the earlier part. So I'll send you some DBP type of problems as well as some questions from the modules to work out. Okay, so that's it for today, people. Thank you.